Hey guys, so today we're going to be walking through Chapter 11 for your Math 200 class, which is about inferences on two samples. So before we get started, I want to show you the flowchart that is in the last section so we can kind of see where we're going because there are a lot of different moving pieces for today. So we're going to be doing hypothesis testing and confidence intervals for four different things. The first is we're going to do proportions, just like we had before. But now the difference is we're going to talk about the difference between dependent and independent sampling, and we have different methods for each. So when we have dependent sampling, we calculate this test statistic here, which we'll talk about. When we have independent sampling, we calculate this test statistic down here. And then we also can talk about the mean, and again, we can talk about independent or dependent sampling. So our test statistics are different for those as well. So I just kind of wanted to mention where we're going so you can sort of see all of the different moving pieces we have. But basically the main idea is we're going to have confidence intervals and hypothesis testing for means and proportions for dependent and independent sampling. So the first thing we're going to talk about in section 11.1 is the inference about two population proportions. So we first need to go through some definitions. So a sampling method is considered independent when the individuals selected for one sample do not dictate which individuals are to be in the second sample. Now dependent is the exact opposite of that. A sampling method is dependent when the individuals selected to be in one sample are used to determine the individuals in the second sample. Dependent samples are often referred to as matched pairs sample. So matched pairs sample could be things like twins that are paired together or a husband and wife, or oftentimes it's just an individual that's matched against him or herself. So possibly they have a measurement taken before something happens and then after something happens. And that would be an example of a matched pairs design as well. So let's look at these examples here. So for the first one, a researcher wants to know whether the price of a one-night stay at a Holiday Inn Express is less than the price of a one-night stay at a Red Roof Inn. She randomly selects 8 towns where the location of the hotels is close to each other and determines the price of a one-night stay. So for this one, it's going to be dependent since the 8 Holiday Inn Express hotels can be matched with one of the 8 Red Roof Inn hotels by town. So they're matched together. So depending on which Holiday Inn Express the researcher chooses, the Red Roof Inn also goes with that. Now, if we read the second example, a researcher wants to know whether the state quarters introduced in 1999 have a mean weight that is any different from traditional quarters. So he randomly selects 18 state quarters and 16 traditional quarters and compares their weights. Now for this example, the sampling method is going to be independent since the state quarters which were sampled had no bearing on which traditional quarters were sampled. So let's look first at a hypothesis test regarding the difference between two population proportions. So to test hypotheses regarding two population proportions, P1 and P2, we can use the steps that follow provided that a couple of things are true. So samples are independently obtained using simple random sampling. And then this qualification that we had before where n times p times 1 minus p had to at least be 10 has to be true for each of our population proportions. n1 times p1 hat times 1 minus p1 hat has to at least be 10, and the same is true for the second population proportion as well. And then the same thing has to be true in terms of independence. We can't take more than 5% for either of our populations. So step 1 is to determine the null and alternative hypotheses. The hypotheses can be structured in one of 3 ways. So these look pretty similar to the previous chapter, but in this case our null hypothesis is that the two proportions are equal, so P1 equals P2. Now that's kind of the assumption that we're working under, and then the two-tailed test would be that they are not equal. The left-tailed test would be that P1 is less than P2, and the right-tailed test would be that P1 is greater than P2. P1 is the population proportion for the first population, and P2 is the population proportion for the second population. So step 2 is to select a level of significance, which is alpha, based on the seriousness of making a type 1 error. And then step 3, just like it was last chapter, is to compute the test statistic. Now, the test statistic in this case is kind of nasty looking. It's a z statistic because we have proportions, and we're taking P1 hat minus P2 hat divided by the square root of p hat times 1 minus p hat times the square root of 1 over n1 plus 1 over n2. And p hat, this value right here, is found by taking the number of successes in each of our groups and dividing by the number in the sample in each of our groups. So we take total successes, total groups. This is our pooled estimator. So we have to calculate this first, and then we have to use our formula up here to calculate the z-statistic. So if you have a left-tailed test, the area is just going to be to the left of z-naught. If you have a two-tailed, sorry, that was for left-tailed, I think I might have misspoke. So left-tailed, you find the p-value by finding the area to the left of z-naught. Two-tailed, you take the sum of the area in both of the tails. So you're going to take 2 times your value to get your p-value. And right-tailed, you're finding the area to the right. Or you can use technology to obtain the test statistic and the corresponding p-value. And I'm going to show you how to do this in StatCrunch because it's particularly nasty to do by hand, so I wouldn't really recommend it. Now, if p-value is less than alpha, you reject your null hypothesis, and then you go ahead and you state a conclusion. These are the same steps as they were in the previous chapter. So here's an example for hypothesis testing with 2 proportions. So an economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. He obtains a random sample of 800 urban households and finds that 338 of them have internet access. And he also obtains a random sample of 750 rural households and finds that 292 of the rural households have internet access. So we want to go ahead and test the economist's claim at the 0.05 level of significance. So first we're going to verify that the requirements are satisfied. Now it said that we used simple random samples, so that part is good. The number of successes for, I think this was urban, yes, is 338 out of 800 total. Number of successes for rural was 292 out of 750 sampled. So our P1 hat is going to be the 338 out of the 800, and our P2 hat is going to be the 292 out of the 750. And we have decimal estimators for each of these, 0.4225 and 0.3893. And then we can check that N1 times P1 hat times 1 minus P1 hat is at least 10, which it is. So if we take our 800 that were sampled times 0.4225 times 1 minus 0.4225, we end up with 195. And then if we do the exact same thing for our second population, we end up with 178, which is both are greater than or equal to 10, so that's fine. And then the sample sizes are definitely going to be less than 5% of our population, so that part is good as well. So the first step is to determine the null and the alternative hypothesis. So our null hypothesis is always going to be that the 2 proportions are equal. So P1 equals P2. Now in this case, the researcher thought that the percentage of urban households with internet access was greater than the percentage of rural households. So the alternative hypothesis is going to be that P1 is greater than P2. Now, one important thing to note is here's our null, here's our alternative. There is another way to write this as well. So if you think about it, if you subtract P2 from both sides, you would get P1 minus P2 equals 0 as your null hypothesis, and you would get P1 minus P2 is greater than 0 for your alternative. These 2 statements are exactly equivalent, and the reason that I point that out is because this second option here is how StatCrunch takes the null and the alternative. Now, the level of significance in this case is just 0.05. So by hand, this is a particularly nasty calculation. So I'm going to show you how to do it, but we're also going to replicate this in StatCrunch. So at this point, you might want to pause the video and see if you can replicate these numbers, very carefully plugging them into your calculator. But the pooled estimate is going to be found by taking the number of households with the internet access, which was the 338 and the 292, and dividing by the total, which was the 800 plus the 750, and we get a pooled estimator of 0.4065. And the reason that we do this is because we use it down here in our test statistic. So the test statistic looks something like this, and this is using that formula that was a couple of slides back. We get a value of 1.33 for our test statistic. Now, this is a right-tailed test, so what we're going to do, we have a z-statistic, so I'm going to go ahead and minimize this a little bit, pop over to my tables, and I want my normal table. I'm going to look up 1.33 on here. So here's 1.3, and then, let's see, I'm going to zoom a little bit. All right, 1.33. So here's 1.30, 1, 2, 3.9082 should be my value there. Now, I have a right-tailed test. So when you have a right-tailed test, you're trying to find the area to the right of 1.33. Anytime you have a z-score and you're trying to find the area to the right, you need to subtract your table value from 1. So I do 1 minus 0.9082, and I end up with a p-value of 0.092. Now in StatCrunch, you're going to see this is much, much nicer. So let me pop open StatCrunch real quick here. Oops, wrong window, sorry about that. This is what I want. Let me scoot this over a little. Okay, so in StatCrunch, we're going to do a very similar thing as what we did in Chapter 10, except remember when we selected one sample, now we have two samples. So I have proportion stats, and in this case, I'm going to select two samples, if it lets me. And in this case, I have a summary of my data. Now over here, I have kind of information recalled from the problem. So for my first sample, I have 338 out of 800 with internet, and for the rural, I had 292 out of 750. And then for this one, I want P1 minus P2 greater than 0. I have a right-tailed test. So I click compute, and this is the value that I get here, 1.33. This should look fairly familiar. That was our z-stat, and our p-value of 0.092. So this matches with the values that we got using the by hand method as well. But you'll notice this is much, much easier. That test statistic is very, very nasty, and I would not recommend calculating it by hand. So step 4 is to determine what to do based on your p-value. So in our case, our p-value is 0.092, which is greater than the level of significance of 0.05, so we're going to fail to reject the null hypothesis. So we would say that there is insufficient or not sufficient evidence at the alpha equals 0.05 level to conclude that the percentage of urban households with internet access is any greater than the percentage of rural households with internet access. Okay, now we're going to be dealing with the exact same type of problem, except we're going to look at a confidence interval. So this is two population proportions again. This is for independent sampling. So we know that in the last example we had independent sampling as well, because we were talking about, if we go all the way back here, rural and urban households. So selecting one particular urban address has absolutely nothing to do with one particular rural address. They're not paired in any way. So we have independent sampling there, and that's what we're going to deal with here. So the same three things have to be true. So I'm not going to go through these again. We have to have independence. We have to have our sample size times our proportion times 1 minus our proportion being at least 10 for both of our samples, and we have to have simple random sampling independently obtained. So our confidence intervals are created using these formulas here, and again, these are not particularly nice. Okay, so I'm going to show you how to use StatCrunch to actually calculate these intervals, but the lower bound and the upper bound are going to be exactly the same, except one has a subtraction symbol, one has an addition symbol. So what we do is we take p1 hat minus p2 hat, and then we add and subtract our critical value multiplied by this kind of nasty looking thing here, where we have square root of p1 hat times 1 minus p1 hat over n, 1, so it's our sample size for our first proportion, plus p2 hat times 1 minus p2 hat over n2, and it's the square root of that entire thing. So we have our same example here, all right? Economist obtains a random sample of urban households, rural households, and in this case we want to find a 99% confidence interval for the difference between the proportions. So what we do is we've already verified the requirements, so we don't need to do that again. But if you recall, our P1 hat is 338 out of 800, which was 0.4225, and our P2 hat was 292 over 750, which was 0.3893. So what we want to do is option one would be to use this formula here. And I'm just not going to go through it because it's very tedious, time consuming to put in your calculator, really easy to mess up. What I want to focus on is showing you guys how to do it in StatCrunch. So for today's demonstration, we're just going to use StatCrunch, and I'm going to go back in here, and I select exactly the same thing that I did before. And really, I could just change my hypothesis test, but I want to show you guys how to do it from scratch. So again, I have stats, I have proportion stats because I'm talking about proportions, I have two samples, and I have summaries of my data. So I have 338 successes out of 800 and 292 successes out of 750. And instead of wanting a hypothesis test, in this case I wanted a confidence interval. And in this case, I think it asked me, let me double check, but I think it wanted a 99% confidence interval. So I go ahead and select 99% confidence, and I click compute here. And what you'll see is it gives me all kinds of stuff. It gives me the sample difference, which would be the difference between P1 and P2. It gives me the standard error and the lower and the upper limits. So in order to interpret this, I just use my lower and my upper limits, and I can actually say that we are 99% confident that the difference between the proportion of urban households that have internet access and the proportion of rural households that have internet access is somewhere between negative 0.03 and a positive 0.10 if we round. Now, one really important thing to note is that this interval actually contains a value of 0. So one of my lower bound is a negative number, my upper bound is a positive number. So in my interval, I actually have the value of 0. So what that would indicate to me is that we're unable to conclude that the proportion of urban households is any different or particularly any greater than the proportion of rural households, because the difference could potentially be 0 based on our confidence interval. Now, the fact that we created a 99% confidence interval here and we did a 95% hypothesis test, alpha was 0.05, could lead to different conclusions. But if you select a 95% confidence interval and you're conducting a hypothesis test with a 95% level of significance, you're going to reach the same conclusion. So the important thing to do is with your confidence intervals to double check and see if they contain 0. And if they do, it means that there is potentially no difference. Okay, now let's take a look at a slightly different hypothesis test. So this again is two population proportions, but in this case we have dependent samples, which is kind of a different situation. So we're going to do this one just using the by hand method, and we're doing something called McNemar's test, and it's a test that can be used to compare two proportions where we have matched pairs data. So we have dependent samples in this case. So in the other case, the rural and urban, like we mentioned, the one rural household has nothing to do with the one urban household. In this case, we have matched pairs data, so it's going to be a slightly different setup. So in order to test hypotheses regarding two population proportions, P1 and P2, where the samples are dependent, we want to make sure that we go ahead and we arrange our data in this contingency table, where we have successes and failures for, we call them treatment A and treatment B. Typically these are like some kind of responses that we've recorded. So we have successes and failures in each, and typically your data is already going to be set up in this kind of fashion. So we're going to use the steps that follow, provided that a couple of things are true. Samples are dependent and are obtained randomly, and then the total of number of observations where the outcomes differ has to at least be 10, meaning if we go back a slide, we have success failure and failure success. When we add these two cells together, we should get at least 10 observations in between those two buckets. And then we determine the null and the alternative hypotheses. So the null hypothesis is going to be that the two proportions are equal, and the alternative is going to be that the two proportions differ. We're always going to do a two-tailed test for this particular setup. And then we go ahead and we select a level of significance based on the seriousness of making a type 1 error, and then we compute our test statistic, which in this case is not too bad. Okay, this isn't too bad to set up. Basically, you take the absolute value of the difference between F12 and F21, which, if we scroll back here, those are our kind of disagreeing cells where we have failure success and success failure. then we subtract 1 from that, and then we divide by the square root of the sum. Then we go ahead and we use our normal table to determine the p-value. Now, our z statistic, in this case our test statistic, is always going to be positive because of the fact that in our numerator we have an absolute value, and in our denominator we have a square root. So we're going to be dividing a positive number by a positive number. Now, we're going to go ahead and find the area to the right of z0, which is going to be 1 minus our table value, and then we're going to have to double this area because we're talking about a two-tailed test. And we'll look at an example with actual numbers in just a second here. Now, step 4 should look familiar. If our p-value is less than alpha, we reject h0, and step 5 is to go ahead and state our conclusion in a full sentence. So let's look at this example here. A recent general social survey asked the following 2 questions at random to a sample of 1,483 adult Americans. And this is under the hypothetical scenario that the government suspected that a terrorist attack was about to happen. The first question was, do you believe the authorities should have the right to tap people's telephone conversations? And question 2 was, do you believe the authorities should have the right to detain people for as long as they want without putting them on trial? So the reason that this is matched pairs is because we have 2 questions being asked of one particular person, and this was done 1,483 times. So if I were asked this first question, for example, I would also be asked the second question. So I matched with myself in this case. Now, the results of the survey are shown below. So we have tap phone and detain. We have agree, disagree, agree, and disagree. And we want to know if the proportions who agree with each scenario differs significantly. We're going to use the 0.05 level of significance. Now, the sample proportion of individuals who believe that the authorities should be able to tap phones is going to be found by taking all of the people who agree with tapping, which would be the 572 and the 237, putting those together, and dividing by the total. So we have 54.55% of people who believe that authorities should be able to tap phones. In terms of the other question, the right to detain people, we would take all of the people who agree with detaining, which would be 572 and 224, put those together, and divide by our same total. We get only 53.67%, so a little bit less, but we want to determine if this is significant. So what we want to determine is whether the difference in the sample proportion is due to sampling error or due to the fact that the population proportions are actually different from one another. So the samples are dependent and were obtained randomly. The total number of individuals who agree with one scenario but disagree with the other, that was our 237 and our 224. That has to be at least 10, which is not an issue here, is 461. So that's not a problem, so we can go ahead and proceed with the test. So step 1 is to set up our hypotheses. They're always going to be the same. In this case, we have PT equals PD. We're calling this for the T for telephone and D for detain. And the alternative hypothesis is going to be that the 2 are different. So P sub T is not equal to P sub B. Now the level of significance is alpha equals 0.05. Our third step is to calculate our test statistic. So this is a z statistic, and it's found by taking kind of those 2 mismatched pairs, so the agree, disagree, and the disagree, agree, subtracting them, taking the absolute value, and then subtracting 1 from that. And you'll notice because of the properties of absolute value, it doesn't actually matter which one of these comes first. Same thing is true down here. For addition, we can add in either order. It's not going to change in our answers at all. So it doesn't matter which one comes first as long as you're using the same 2 values. We get a value of 0.56. So what we would like to do is we want to go to our normal distribution table. Let me pull that up here. And I'm going to look for 0.56. So 0, 1, 2, 3, 4, 5, 6. That's going to be 0.7123, I believe. So if I take 0.7123, and this is not shown here, I apologize for that. Get a little calculator here. So I'm going to take 1 minus 0.7123, because that's going to give me the area to the right. And then I'm going to go ahead and double that. I get 0.5754. Now, the reason that I doubled that was because I am talking about a two-tailed test. So I always have to take my probability and multiply by 2. So again, I looked my value up on my table. I did 1 minus to get the area to the right, and then I doubled that value in order to get my p-value. Now, step 4, that would be to use my p-value to make a conclusion. So since my p-value is greater than alpha, we're going to fail to reject the null hypothesis. So I can say that there is insufficient evidence at the alpha equals 0.05 level to conclude that there is any difference in the proportion of adults who believe it is okay to tap phones versus people who believe that it's okay to detain people for as long as they want without putting them on trial, in the event that the government believed a terrorist plot was about to happen. So there's no difference between the two based on this sample data. Now, we can also do sample size calculations in this chapter. So the sample size that's required to obtain a confidence interval with a given margin of error is given by the following formula. And it looks a little bit nasty. It's not too bad to actually use, but we take p1 hat times 1 minus p1 hat plus p2 hat times 1 minus p2 hat, and we multiply that by the critical value over the margin of error squared. And this, just like our sample size calculations from a couple chapters ago, needs to be rounded up to the next integer. Now, that's if prior estimates are used. Now, if prior estimates are unavailable for some reason, then the sample size is calculated using this even nicer looking formula where we have 0.5 times the critical value over the margin of error squared. And that's also rounded up to the next integer. Now, the next thing you'll notice is we just had one sample size before. In this case, we are now taking 2 different samples because we have 2 different proportions that we're interested in. So in this case, you have to ask that many people from each group. So for example, if I did a calculation and I found out that I needed a sample size of 100, I don't need 100 total, I need 100 from my first group and 100 from my second group. So I actually need 200 total. So let's look at this example here. A doctor wants to estimate the difference in the proportion of 15 to 19-year-old mothers that received prenatal care and the proportion of 30 to 34-year-old mothers that received prenatal care. So we want to know what sample size should be obtained if she wishes the estimate to be within 2 percentage points, 95% confidence, and then for A, she's going to use results from the National Vital Statistics Report, which indicates that 98% of the 15-year-olds, or 15 to 19-year-olds, and 99.2% of the 30 to 34-year-olds receive prenatal care, and then we're also going to do the same calculation, not using any prior estimates at all. So we know that our margin of error is 0.02, that's our 2 percentage points, and we wanted 95% confidence. Now, if you recall from 2 chapters back, 95% confidence goes with a critical value of 1.96. Our P1 hat is 0.98, that's the proportion of 15 to 19-year-old mothers that we were using who got prenatal care, and 0.992 is our P2 hat, that's our proportion of, I think it was 30 to 34-year-old mothers who received prenatal care. So we have to use this formula. Again, this looks a little nasty, but we're just going to take our 0.98 times 1 minus our 0.98 plus our 0.992 times 1 minus 0.992, and then once we have that, we multiply that by 1.96 over our margin of error of 0.02 squared. And you might want to pause the video for a minute to go ahead and try this, but you should get a sample size of 264.5. So we always have to round up regardless of what this number is. So we need to sample 265 people from each group. So again, it's from each group. So 265 15 to 19-year-olds and 265 30 to 34-year-olds. Now, if we use no estimate at all, so no prior estimate, we're going to use this formula here, which basically maximizes our sample size. So we have 0.5 times 1.96 over 0.02 squared, which gives us a much, much larger sample size. So if we're not using prior estimates, we have to take a much larger sample. In this case, we have to take a sample of 4,802 15 to 19-year-olds and 4,802 30 to 34-year-olds. Okay, Now let's take a look at section 11.2, which is the same sort of thing, so confidence intervals, hypothesis testing, but this time we're going to talk about two different means. So 11.2 particularly talks about the inference of two means for dependent samples. So the basic concept is that statistical inference methods on matched pairs data use the same methods as inference on a single population mean, except that instead of just having one mean, we look at the differences. So, in order to test hypotheses regarding the mean difference of matched pairs data, the following has to be true. The sample has to be obtained using simple random sampling, the sample data have to be matched pairs, and the differences need to be normally distributed without any outliers, or the sample size has to be large enough, n greater than or equal to about 30. Now, in terms of our steps in hypothesis testing, you'll notice a lot of these things are exactly the same. Our test statistics going to be a little different. Our setup of our null and our alternative hypotheses are also going to be a little different. So in this case, we're looking at mu of D, which is the population mean difference of the matched pairs data. Now, under the null hypothesis, we assume that this value is 0, meaning that there's no difference at all. Our two-tailed, our left-tailed, and our right-tailed tests test that it's something other than 0. So if we're not sure which direction, we would say not equal to. If we think that it's less than 0, we would do a left-tailed test. Greater than 0, we would do a right-tailed test. Now we go ahead and we select our level of significance, and we compute our test statistic, which isn't too bad to compute. It's a t statistic since we're talking about a mean, so we don't know our population standard deviation. And it's found by just taking d bar, which is the average difference, and dividing by s of d, which is the standard deviation for the difference data, over the square root of n. And that's going to follow a student's t distribution with n minus 1 degrees of freedom. And then we use table 6, which is our t-distribution table, to approximate the p-value. You should be fairly comfortable with this by now. A left-tailed test finds the area to the left, a right-tailed test finds the area to the right, and a two-tailed test, the p-value is found by taking the sum of the area in both of the tails. Now we can also use StatCrunch in order to kind of do steps 3 and 4, and it's pretty easy. It's just stats, t-stats, so that was the same place that we went before for means, but instead of selecting one sample or two sample, you actually select paired because your data is paired. Now, if the p-value is less than alpha, you go ahead and you reject the null hypothesis, and then you state the conclusion in a full sentence. Now, one important thing to note is that the procedure is robust, which means that minor departures from normality won't adversely affect the results. But if you have small samples and you have outliers, you really should not use this procedure. Okay, so let's take a look at this data right here. We have data that represents the cost of a one-night stay in a Hampton Inn and then in a La Quinta Inn. And it's a random sample of 10 different cities, and we want to test the claim that Hampton Inn hotels are priced differently than La Quinta, so not necessarily more than or less than, just differently. And we're going to use alpha equals 0.05 level of significance. So we have all of our cities here, we have Hamptons and La Quintas. This is paired because when we choose a city and we choose the Hampton, the La Quinta that is nearest also goes with that value. So to test the hypotheses, we first compute the differences, and then we verify that the differences come from a population that's approximately normally distributed without any outliers. And this is if we're doing it by hand. So if we take a look here, Hampton minus La Quinta, for the first one, we would take 129 minus 105, and we get a $24 difference for that one. And then for the next one, we'd take 149 minus 96, and we'd end up with a $53 difference. So we have all of these values here. You'll notice there's only one that's negative. That would be for San Diego. It was only 109 for the Hampton, and it was more expensive for the La Quinta at 119. So that difference is negative. Now, if you use just the test statistics, or sorry, just the descriptive statistics, you can find that D bar, that's just the average, is a 51.4 or $51 difference basically, and the standard deviation is about $30.83. Now, if we take a look at a normal probability plot and a box plot, we can see that there's no violation of the normality assumption, and we have a small sample, so we want to make sure there aren't any outliers, and there are not, so that's fine as well. So step one is to set up our null and our alternative hypotheses. The null hypothesis is that the mean difference is 0, and the alternative is that the mean difference is not 0. So again, this one wasn't left-tailed or right-tailed, it was just that the prices differ in some way. Now, the level of significance is found, or was just stated to be 0.05. So we calculate our test statistic by taking our 51.4, which was our average difference, and dividing by S, which was our standard deviation of our difference data, which was 30.8336, and dividing that by the square root of n. In this case, n is the total number of pairs, so in this case we had 10 pairs. And we get a t-statistic of 5.2716. So what we need to do is we need to go to our t-distribution table. So I'm going to scroll down a little bit. Here's my t-distribution. Now, first thing you want to do is locate the correct degrees of freedom. In this case, I have 9 degrees of freedom, so I'm going to go to 9, and I'm going to just scroll up, so that's like the last thing in our row. And what you want to look for is 5.27. And again, you're going to find bounds just kind of like you did before. So if we kind of scroll our way across, it's getting larger and larger. Sorry, not doing a very good job of scrolling very straight. But this is our 9 degrees of freedom. The largest value that we have here is 4.781. So the value of 5.27 is way off of our chart. Okay, so if we use technology, you would get a value of 0.00026 multiplied by 2 because it's a two-tailed test. So using technology, it's only 0.00052, that's our p-value. So only 5 samples in 10,000 would yield results that are as extreme or more extreme than this one if the null hypothesis were actually true. So it's very, very rare. So in this case, we would go ahead and we would reject the null hypothesis, and we would conclude that there is sufficient evidence to conclude that Hampton Inn hotels and La Quinta hotels are priced differently in some way. Now, I want to go back one slide and show you how to do this in StatCrunch as well, because it's very easy. So let me move this out of the way a little bit, pop open StatCrunch. You'll notice I already have my data in here, and this should not say agree, disagree. This is a typo here. But if you look, I have Hampton prices and La Quinta prices. So I'm going to go into stats, t-stats, and I have paired data. My first sample was Hampton. My second sample was La Quinta, so I just select those. And then I want to perform a hypothesis test, mu of d equals 0 versus mu of d not equal to 0. So this is already selected for me. If I wanted a left-tailed test, I would select the less than. If I wanted a right-tailed test, I'd select greater than, but I just want this two-tailed test here. So I do compute, and I get that same test statistic and a very similar p-value. So I would come to the exact same conclusion using StatCrunch as well. Now, I can also construct confidence intervals for matched pairs data, and this is done just by taking d bar, which is the average of your differenced data, and adding and subtracting a critical value multiplied by the standard deviation of your difference data over the square root of n. So this looks very familiar to you already. We just have a critical value that we have to find in order to construct our confidence interval. So the interval is exact when the population is normally distributed, but it's only approximately correct for non-normal populations, provided that n is large. This is just one kind of important note and distinction that we want to make here. So let's take a look at an example for the confidence interval. So we're going to deal with that same data to just kind of make our lives a little easier. We should end up with a conclusion that kind of matches our previous conclusion, but we want to construct a 90% confidence interval. We already know that the data comes from, or the difference data comes from a population that's normally distributed, no outliers. If you recall, our D bar value was 51.4 and our standard deviation of our difference data, so this was the mean, our standard deviation was 30.8336. So our critical value is going to be found just by looking at table 6. So let me pull my table back up here. And I'm going to zoom out a little bit, kind of too close there. So I have alpha equals 0.10. So alpha over 2 is going to be 0.05. And I have 9 degrees of freedom. So I look at 9 degrees of freedom, 0.05, and I get 1.833 as my critical value there. So that's going to be the value that I'm going to use to construct my confidence interval. So my lower bound, when I take my D bar, which was 51.4, and I subtract 1.833, which was my critical value, multiplied by the standard deviation from my sample over the square root of n. Make sure you follow order of operations and do this multiplication and division first. I get $33.53 as my lower bound, and my upper bound, same thing but with a plus instead of a minus, ends up being $69.27. So we can say that we are 90% confident that the mean difference in hotel room price for, this should be, I don't think it was Ramada, it was Hampton Inn, sorry, Hampton Inn versus La Quinta Inn is somewhere between $33.53 and $69.27. So you'll notice that this interval does not contain a value of 0. So we can make the same conclusion where we decide that there is a difference in the prices between those two hotel rooms. Now in StatCrunch this is very easy as well. We can do this the exact same way that we did this before, which really I already have my hypothesis test open. I could just edit this a little bit. But if I go to T-stats, I have paired data. Sample 1 is my Hampton data. Sample 2 is my La Quinta data. And this one I want a 90% confidence interval. So I just select the confidence interval radio button and I do 90 and I do compute. And if I move this over, that gives me a lower limit of 33.52 or 53 and 69.27. So it's the same values that we got right here. Okay, and the next thing we're going to look at is in section 11.3, inference about two means for independent samples. So 11.2 was all about inference of two means where we had dependent samples, meaning we had matched pairs data. So this one we're going to look at means, but for independent samples. So let's suppose that a simple random sample of size n1 is taken from a population with a known mean of mu1 and an unknown standard deviation of sigma 1. And in addition, a simple random sample of size n2 is taken from a population with an unknown mean of mu2 and an unknown standard deviation of sigma 2. If the two populations are normally distributed, or the sample sizes are large enough, meaning each sample size is at least 30, if those two things are true, then we can go ahead and calculate a test statistic, t, just by taking x1 bar minus x2 bar, minus this mu1 minus mu2. It's good that it's included here because this is technically correct, but under the null hypothesis, we're going to assume that the mean difference is 0. So when we actually go to calculate our test statistic, this is always going to be 0 here. And then we divide by the square root of S1 squared, which is our sample standard deviation from our first sample, over N1, which is the sample size for the first sample, plus our sample standard deviation squared from our second sample over N2, which is our sample size for our second sample. And this is going to follow a student's t-distribution with the smaller degrees of freedom between the two. So what we do is we look at sample sizes for each, and then we use the smaller number of degrees of freedom. So a couple of things have to be true in order for us to actually test hypotheses and also in order to create confidence intervals. Samples need to be obtained using simple random sampling. Samples need to be independent. The populations need to be large enough or normally distributed, and then the sample size can't be more than 5% of your population size. So the steps in hypothesis testing, you should be very familiar with these at this point, but of course this varies depending on what we're talking about. In this case, we're comparing two means from different samples. So we have our null hypothesis being mu1 equals mu2, so the two being the same. And the alternative hypothesis would be that mu1 is not equal to mu2, mu1 is less than mu2, or mu1 is greater than mu2, depending on what kind of test you want to set up. And then the second step, of course, is to select a level of significance, compute that test statistic that we talked about earlier. Now, it's not too bad to do by hand, but for our demonstration today, we're going to use StatCrunch for this step and the next step. Now, if you were doing this by hand, you would go ahead and you'd use table 6 in order to approximate the p-values. And this would be done basically doing the exact same thing that we did in the last section, where we take, if we have a two-tailed test, we take 2 times our probability. If we have a left-tailed test, you just look it up on your table. If you have a right-tailed test, you have to do 1 minus the table. So in this case, you just have to kind of make sure that your p-values are making sense. But we're going to use StatCrunch today in order to calculate our p-value and our test statistic. Now, in StatCrunch, there are a couple of things that I want to point out. The first is that we're still using t-stats because we're talking about our students' t-distribution because we're using our sample standard deviation to estimate our population standard deviation for our mean. We have 2 samples in this case, and we're going to either use with data or with summary depending on what we have. And then the important thing that I have here is that there's a little pool variances box that's going to be checked. In order to get the correct answers for my math lab, you're going to want to uncheck that box. Now, if the p-value is less than alpha, you're going to reject the null hypothesis, and then you're going to go ahead and you're going to state a conclusion. Now, this procedure is robust, which means that minor departures from normality are not going to adversely affect the results. However, if you have small samples or if the data has outliers, really you should not use this procedure. So what we're going to do is we're going to look at state and traditional quarters. This is an example that we talked about much earlier in the presentation. So a researcher wants to know whether state quarters had a weight that is more than a traditional quarter. So he goes and he randomly selects 18 state quarters and 16 traditional quarters. Now, these quarters have absolutely nothing to do with one another, so they're independently obtained. And the data looks like this. So we have our state quarters, we have our traditional quarters. And we want to test the claim that state quarters have a mean weight that is more than the traditional quarters. Now, a little note here, if we look at a normal probability plot of state quarters, it indicates that the population could be normal, and the same is true of traditional. So what we're going to do is we're going to set up our null hypothesis that says that mu1 equals mu2. So we were working under the assumption that the means are the same. And our alternative hypothesis is going to be that mu1 is greater than mu2. State quarters weigh more than traditional. And we're going to use a 0.05 level of significance. So at this point, I'm going to go ahead and pop open StatCrunch because it's going to be pretty helpful for us here. So let me close some of this stuff. If you see, I have state quarter and traditional quarter data already in here. So I'm going to go to t-stats, because I have a mean, so I'm using the t-distribution. I have 2 samples, and I am given data in this case. I don't have summaries, I have the actual data. Now my first values are the state quarters, and my second values are the traditional quarters. And again, I want to uncheck pool variances. Okay, so go ahead and uncheck that. And in this case, I want a hypothesis test. I want a right-tailed test, so I want greater than. And then I go ahead and do compute. And let me go ahead and go to the next slide here. If we take a look at what I'm given, let me move this over. I have a test statistic of 2.54-ish with a p-value of 0.0086, which is pretty small. So the p-value in this case is going to be less than alpha. So we're going to go ahead and reject our null hypothesis. So we can actually conclude that there is sufficient evidence at the 0.05 level to conclude that state quarters do in fact weigh more than a traditional quarter. Now I'm going to leave this, well, let's see, make this a little larger. I'm going to leave it a little small because we're going to come right back to StatCrunch in a minute here. But we can also construct a confidence interval using pretty much the exact same rules, slightly different formula, obviously, because we're constructing a confidence interval. But the same conditions have to be met, so I'm not going to go through those. Our lower and our upper bounds are found by taking the difference between the two means and adding and subtracting the critical value multiplied by the square root of our sample standard deviation squared over its sample size plus the other sample standard deviation squared over its sample size. Now, the critical value in this case needs to be found using the smaller number of the degrees of freedom. And again today, just like the last one, we're going to use StatCrunch to construct our interval. So I'm going to use the exact same thing that I did before. I'm going to construct a 95% confidence interval this time. We already verified that everything was met, so I'm just going to show you how to do this. So I could just edit this if I wanted, but let me start over for you. So I'm going to do stat. I have t-stats, 2 samples with data. My first values are the state quarters. My second values are the traditional. I want to uncheck the pool variances box. And this time I want a confidence interval 95%. And I do compute. And if I go over here, it gives me a bunch of information. I care most about the lower and the upper limits. So I can say that we are 95% confident that the average weight of the state quarters is between 0.010 and 0.0956 ounces more than the average weight of the traditional quarters. Now you'll notice that the interval does not contain 0 in this case, so it is possible to make that same conclusion where we were able to conclude that state quarters actually weigh more than traditional. Now if the interval did contain 0, it means that maybe there's no difference between the two. But since the interval does not contain 0, we know that there is a significant difference between the weight of state quarters and the weight of traditional quarters. So to just kind of summarize again, this is that same flowchart that I showed you at the beginning. In this chapter, we had proportions and we had means and we had dependent and independent sampling for each. So when we had proportions for independent sampling, we used a z-statistic. That was the first thing we did. And then when we had dependent sampling, we used we used a z-statistic as well, but this one was done differently. This is where we had our data set up in our contingency table and we were conducting McNemar's test. Now with our mean, when we had independent sampling, we used this right here. We used our t-statistic. And when we had dependent sampling, we basically calculated the t-statistic for our difference data. So we used the differences between our paired observations, and then we calculated the test statistic that way. So that is it for chapter 11. Please feel free to let me know if you have any questions.